Okay, so obviously I am terrible at estimating how much time it is going to take me to get through everything. I'm working on it, okay? Sorry this is way more videos than you were expecting, but hopefully you found this stuff to be interesting because I just think it's super cool and super interesting. So hopefully you do too. So in this picture, these are two individuals who have achondroplasia. So if a person has achondroplasia, which is a dominant disorder, it means that they have a heterozygote genotype, and their phenotype is that they have achondroplasia. If it's like you or I, we're all of normal height, we do not have achondroplasia, therefore we are homozygous recessive. Remember that individuals who are homozygous dominant for achondroplasia are spontaneously aborted or miscarried. Okay, so dominant alleles that cause lethal diseases are a lot less common than recessive lethal diseases. And what do I mean by that? Because just now I was talking about homozygous dominant, in that case being lethal. I mean disorders that we know are going to kill people that are dominant disorders. They're going to be much less likely to be passed on than recessive ones that we know are lethal and will kill people. The reason for this, or one of the reasons for this, is that the dominant lethal alleles can't be carried by individuals without affecting the individual. So your heterozygote individuals are going to be affected. So therefore, they know that they have it, and if they don't, it's not that if they don't know, but if it's a really lethal disease, and they a lot of times will just be spontaneously aborted, even if they're heterozygotes. So even if you can exist as a heterozygote with this combination of alleles, oftentimes they still don't survive. The female body, and we'll talk about this when we do female reproductive system, but the female body is like amazing at being able to tell if there's something genetically wrong with a fertilized egg, and they will have a miscarriage if they know something's wrong. Even if, like, in your brain, obviously, like, as a woman, like, you don't know anything's wrong, but your body knows. So a lot of times, even if they are a heterozygote individual that could survive with this disease, whatever dominant disease it may be, they are still miscarried a lot of the times. If they're not miscarried, and they do get born, they may not survive to the age of reproduction. So they're either born and they know they have it, and they live long enough to reproduce but choose not to because they don't want their children to have it, or B, they don't even live long enough to be able to reproduce. Like, they don't live long enough to have, like, their first period or anything like that. So if that happens, obviously that allele can't be passed on because the person died before they could pass it on, right? So either way, whether it's that the individual decides that they're not going to have a child, or the baby dies before it's old enough to reproduce, or it is a spontaneous miscarriage, in any case, that trait's not going to be passed on. Whereas with recessive diseases, people carry it without being affected, so they don't even know they have it until they have a child with it. And so any children that they have whatever percentage chance of getting that disease, right? So it's perpetuating that recessive trait. And even if two carriers have a child, 50%, if you do the Punnett square, even if they're just carriers, 50% of their children will also be carriers. So you're perpetuating that recessive allele. That doesn't happen with the case of dominant lethal diseases. Okay, if you hear that sound, that is Maggie chewing a bone right next to the computer screen because she's like that. So one case of lethal dominant alleles being able to survive elimination is if someone with the disease does live long enough to reproduce. And actually this is the case with Huntington's disease, which was that degenerative nervous system disorder that hits at about middle age. By the time people hit middle age and start having these symptoms and get their Huntington's diagnosis, by the time you're doing that, you've already reproduced. You've already had kids. So you've already potentially given it to half of all of your children. Once the deterioration with Huntington's starts, as of right now, it's unstoppable. it's irreversible and is eventually fatal. It's really sad. One of the things that we're hoping that we can fix with CRISPR technology, which hopefully you guys watched that webinar. If you didn't, let me know and I can resend the link because it's really interesting. CRISPR is so fascinating. But this is one of the things that once somebody has it and they know they have it, and it's like the damage is already started, there's nothing that you can do to stop it. And in fact, if a person who has Huntington's gets tested as a child and they find out that they have it, there's still nothing you can do. You can't change it. Once you know it's going to happen, the story's already written for you. If you have those genes, you're going to get it. But again, they already reproduced by the time they even find out that anything's wrong with them. So they've given, at least they had the chance of giving half of their children. So if they had 4 children, there's a high percentage chance that 2 of those 4 are going to have Huntington's. Because remember, if you have Huntington's, if you have a lethal, or if you have a dominant disorder, you only have 1 copy of that allele. And so that 1 copy goes in half of your eggs or half of your sperm, and then the recessive allele, that copy goes to the other half of your egg or your sperm. Right, so it's a 50% chance. So this is definitely another evidence that dominant is not always better. In this case, dominant's worse. But we actually can now do genetic testing to determine if someone has Huntington's. And people who go through things like IVF, which is in vitro fertilization, where perhaps the parents can't get pregnant through normal intercourse, they can take the dad's sperm and the mom's egg, and they can literally make an embryo in a petri dish, and then they can take those embryos and they can implant them into the mother's womb, and then all's ready to rock and roll, right? They can do genetic testing on those embryos to determine if they have things like Huntington's. And the next little thing that we're going to go over in our next summer science will be, I'll talk about all the different genetic testing that they can do and all the different types of tests that are done on pregnant people to determine things about their babies. And then we will talk about genetics that don't follow the natural, well, not natural, it's still natural, but don't follow Mendelian genetics, don't follow the straight dominant versus recessive. We'll talk about things like incomplete dominance and how we get pink flowers. Some of you watched the video, probably most of you that are in summer science watched the video, but we'll do legitimate blood typing, and we'll do the other types of dominance and the other types of inheritance patterns. Yeah, so here is a little question if you want to test your understanding of dominant or recessive disorders. If Peter is a 30-year-old man whose father died of Huntington's disease, if Peter's mother nor older sister show any signs of Huntington's, so we're trying to figure out what is the probability that Peter has inherited Huntington's disease. So pause it, see if you can figure it out, and then press play to learn the answer. So this is how I'm going to work through this. So Peter is a 30-year-old man whose father died of Huntington's. So we know for sure that his dad was a heterozygote, right? Peter's mom doesn't show any signs. So we can be pretty confident that since Peter's mom and Peter's dad probably are around the same age, or were around the same age, then we can assume that Peter's mother does not have Huntington's, right? So we know that she's homozygous recessive. So then you just do a Punnett square with a heterozygote individual and a homozygous recessive individual, and then you see out of those 4 boxes, which percentage of those receives a dominant allele, right? In this case, knowing information about Peter's older sister is in there to throw you off. It's completely and totally unnecessary to know if Peter's sister has Huntington's, because remember, whenever you have these Punnett squares, you're showing the possible offspring for every single time that particular pair has a child. It's not showing you what will happen to 4 children. It's showing you what will happen to any of their children. These are their possibilities, right? So if we do our little Punnett square, we do one heterozygote and one homozygous recessive, right? We can see that there is a 50% chance that Peter has Huntington's. So we won't really know unless we do genetic testing on Peter. And I think that might be the last slide. Yeah, and we'll talk about the new technologies and stuff on the next Summer Science. So I hope you enjoyed. Let me know. Again, please give me feedback. Sorry these are a little bit longer. If they're too long and this isn't really like your thing, let me know. I can try to shorten it to just do like fun facts, but I feel like it's more fun to really give you like all the knowledge. Just let me know. Also, let me know if you guys want to set up maybe like a weekly Zoom date that we can do where we can talk about whatever summer science topic we're on. So yeah. And then last thing, I will put some practice worksheets in OneNote in a new tab in the content library called Summer Science. So you can check that out. And I'll also put this PowerPoint there.